Let's begin. Hey, everybody. Welcome to this presentation. My name is Alex Merced. I'm the head of DevRel at Dremio, and I'm going to be talking about Apache Iceberg, one of my favorite topics. Anyone who's followed me at all on LinkedIn knows that I literally wake up, I talk about data lakehouses and Iceberg, and I go to sleep and I do it again. But yes, we're going to take this presentation to be more of an architectural look. So we're going to take a look at sort of like the guts of how Apache Iceberg works, why it exists, what's the problem it's trying to solve, to get a good foundational understanding of what Apache Iceberg is and why it's so important. I'll be doing another talk tomorrow. We'll go a little bit deeper into the ecosystem of Apache Iceberg, where we'll explore sort of like the specs, how it's evolved this year with V3 and any proposed changes for V4. We'll talk about the catalog specification and a little bit more about like Iceberg table maintenance. All of that will be in tomorrow's presentation as well. So I'll be around. Now let's continue on. Again, I'm Alex Merced, head of DevRel at Dremio. I've been with Dremio for about 4 years now, where basically I've spent the last 4 years just educating and evangelizing the data lakehouse Iceberg space. And in that journey, I've gotten to contribute to several books. Apache Iceberg, the definitive guide from O'Reilly, Apache Polaris, definitive guide from O'Reilly, which just came out. Also did this sort of joint contribution with a couple other companies, Min.io, Confluent, Puppygraph, others. All these three you can get for free. If you scan that QR code, you can just download a PDF copy of all three of those free. And my newest project is architecting an Apache Iceberg Lakehouse. I'm running this book with Manning. This book is less about what is Apache Iceberg, but more like, hey, you've decided you want to go forward with Apache Iceberg, and you're looking to decide, hey, what storage should I use? How do I know what are the different storage options? What's the best one depending on what my use case is? What's the right way to ingest the data? What's the right catalog? All depending on your use case, and kind of first figuring out what are your requirements to begin with. That's just about done. I still have a few more chapters to edit, but I am raffling off codes for a free copy. So if you scan that QR code, that'll let you enter the raffle for that presentation, and I will give the winner their code after the conference. Cool. So now for our featured presentation. Okay, so today we're going to be talking about what is a table format, because that's what Apache Iceberg is, a table format. So we need to understand the category first. Why do we need a new one? Okay, didn't we already have tables? Why do we need a new thing? Okay, how does Apache Iceberg work, the architecture of it? And then we're going to go through some examples of some transactions to actually see like sort of what happens when you do an Apache Iceberg transaction, and what are the benefits of this whole structure to begin with. So to really appreciate this whole like data lakehouse table format thing, let's think about sort of like how traditional data systems have worked up till now. So up till now, generally we've worked with databases and data warehouses. Okay, and we love databases, and we love data warehouses. The reason is because they abstract so many things away for us. For example, how is our data stored? If I put data in Postgres, Postgres handles how that data actually gets persisted onto disk. I don't have to think about, how are all those bits configured, okay? Table format, how does it know the data that is stored? How does it know that this is the sales table, this is the orders table, this is the users table? I don't have to think about that, okay? The system takes care of that for me. Okay, oops, spoilers. Catalog, okay, as far as like, how do I know which tables are available? How do I know that there's a sales, an orders, a users table? Well, built into the system is a catalog that tracks and governs those tables. And at the end of the day, also, I'm able to write like a SQL query or SQL query, or however is the parlance these days. Write a query, have that query string parsed, turn into an abstract syntax tree, then turn into an execution plan, and then have that plan actually executed to give me back my results. How all that happens, I don't have to think about, okay? The system does it all for me. Basically, a database, data warehouse integrates all these things where I'm thinking about like transactional data for like operational systems where the data is generally stored as rows, or if I'm thinking about like analytical systems where the data is oftentimes going to be stored as columns. This all works really well. Problem is that each system does it their own way. Each system decides how they're going to store the data, how they're going to recognize the different tables, and how they're going to organize the metadata for those tables, how they're going to catalog it, how they're going to track access control. All these things are different from system to system. This becomes a bottleneck on the analytics side because we use lots of tools. Nowadays, there's a lot of purpose-built tools that want to talk to the data. And if every tool thinks about the data differently, then what happens, I end up copying the same data across multiple tools, which creates redundancy of copying the data over and over again, which creates costs, creates delays for me getting the data to my actual use case, whether it's a BI dashboard, an AI agent, or wherever I want to use that data. So the idea is, how else can I access my data in a way that allows more of my tooling to actually access it? One approach was an approach called the data lake. Okay, and the idea behind the data lake was, how about we just store the data as a file in a storage layer and just run analytics from there? Okay, so I would get like a storage layer, let's say like an Amazon S3 or an ADLS or Google. I would store the data as files. In the early stages, you think like CSV, JSON files, just run analytics on those. Eventually, you kind of hit a scaling limit there. And eventually, you may move on to like Parquet files, okay, a file format that's really optimized for analytical type queries. And that's all well and good. The problem is, like, I might have a data set that's like 1,000 Parquet files, and my tools don't really understand that this 1,000 Parquet files are a table. Like, they don't think about it in the same way. What I'm interacting with is a file system and a list of files, not a table. Okay, and that has certain limits and certain limitations. And I can use tools like Dremio, AWS Athena, pretty much DuckDB. Literally any tool you can think of that can query data nowadays can go to access that storage layer and query those Parquet files. That's all wonderful, but it's generally going to be mostly read-only. Having to update the data doesn't really give you the same guarantees the database does. When you think about like consistency, about isolation, atomicity, I'm not getting those guarantees. Okay, and then oftentimes governing was a little bit tricky and organizing the data was really tricky, so you ended up with what was called like a data swamp, where it's just, you have the data there, it's just not very usable. So the idea is, when I take a look at this, I've noticed that there's a couple pieces missing. When I think about how the way the databases and data warehouses worked, there's 2 layers that were there that are not here. What happens if I add those layers back in? That's where we get a data lake house, where I can take my data lake using my storage and basically make it feel more like a data warehouse, where the paradigm of how I interact with it is different. I'm not interacting with a storage layer with a bunch of files in it. I'm now interacting with a catalog of tables. Okay, and it feels more like I'm interacting with that data warehouse, where we're thinking like Redshift, Synapse, BigQuery, Snowflake, etc. So since I have a storage layer already, I have tools that can query that storage layer, but what if I add in a table format? What if I add in a way to take those Parquet files and not treat them as 1,000 Parquet files, but treat them as the users table, the orders table, okay, as individual tables, and have a way to track those tables and see who has access to those tables, the catalog. I'll talk more about catalog tomorrow, okay? So we have those 2 pieces. So those 2 pieces are what takes a data lake and turns it into a data lake house, the table format and the catalog. Okay, and again, a table format specifically is just a way to ask the question, sort of, which files in your storage are part of the data set? Okay, hey, there's maybe millions of Parquet files sitting in my storage that belong to dozens, if not hundreds of data sets. How do I know which ones belong to which ones? So originally, as data lakes began to form, there was a tool called, well, first you had Hadoop. So you had like basically commodity storage, so a way to store data across many computers and treat it as one large hard drive very affordably, and you would store data on there. The question is, I would like to write SQL or SQL to run analytics. Originally, you had to use a thing called MapReduce, where you had to write jobs in Java, which wasn't the easiest thing to use. So eventually, someone created something called Hive. And the promise of Hive was, hey, you can run analytics on all that data you have on Hadoop using SQL, but to use SQL, you have to determine what is a table. So the question is, how do I know what is a table? And the answer that Hive came up with was, you point us to a folder, any files in that folder are a table. So if it's a folder of 1,000 CSV files, all 1,000 CSV files are part of the same data set. Or if it's 1,000 Parquet files, all of them are part of the data set. Wonderful. Okay, this works. Okay, now I was able to write SQL. Hive would take that SQL, turn it into a MapReduce job, and run that against my Hadoop cluster and allow me to run analytics against that sort of early stage data lake. Okay? And that was all good. And this provided us a lot of benefits over time. Okay, so again, we're just taking any folder and saying, hey, there's a folder called sales. All the files in the sales folder is the sales table. Now, the pros of this is that Hive became the standard for, and still very much is a very ubiquitous component to a lot of these sort of analytical systems. So in this case, it created a standard. Pretty much every tool still works with Hive and knows how to work with Hive. Okay, this allowed more efficient query patterns in the sense that I can now take advantage of things like partitioning and take advantage, of partitioning. Okay, it was file format agnostic, so Hive didn't really care what was in the folder. If it was CSV files, that was the table. If it was Parquet files, JSON files, whatever it was, it would work. Okay, it allowed some level of atomicity. Okay, so generally what happens is that you have the Hive, but you also have something called the Hive metastore that would track the tables. The thing is that the way it tracked the tables was by tracking directories. So it tracked, hey, this folder is the table, and then these subfolders are the partitions or the subsections of the table. So that means the sort of the most granular thing you tracked was folders. So if one folder is a partition, that was like your granularity for atomicity. So if I wanted to update one record, I'd have to rewrite a whole partition and then swap it out. So that's better than nothing, but still not ideal. Okay? And at the end of the day, it did provide an answer to what is a table. At least we had a way to say consistently what is a data set. So that's nice. But again, smaller updates were inefficient. Again, if I wanted to update one record, I'm still at best atomically updating a partition. Okay, it would be really hard to update multiple partitions, and a lot of this kind of concurrent transaction stuff would be very, very difficult to do safely in Hive. Okay, so again, concurrency, at the end of the day, you'd have to do a lot of directory listing. So in the sense that I would go into a folder and say, hey, I know this folder is a table, but I don't know what files are in that folder yet. I actually have to go in there and list all the files and then iterate through all the files, read the files. All that made those transactions take a lot longer. Okay, because if I had to go through every file, well, it just takes longer. And when it came to partitioning, I'd have to understand the physical layout of the table. So I'll get into this a little bit more later on, but an example would be like, if there was a table that had a timestamp column for like an event of some sort, and then I partitioned that table based on like hour. Well, generally what would happen is that I would have to then create a separate column for like month, hour, year, and partition based on those columns. And the data analyst writing the SQL query would have to know that. Because if they just did a range of timestamps, it would still query the whole table, not just those right subsections or those partitions. So it was really easy to end up with really long running queries if you didn't write that SQL correctly. Okay, and then also you didn't automatically generate statistics. You had to kind of tell Hive every once in a while to go read the table, generate table stats in order to optimize performance. Okay, so overall, better than before, but still some bottlenecks. And Netflix was using Hive, and Netflix was starting to run into some start really feeling these bottlenecks when you think about the level of terabytes and terabytes of data that Netflix has. So they wanted to create a new system. One, they still wanted to make sure that they can get the correct table consistently every time, but they want to have faster query planning. They don't want users to have to worry about this whole like, hey, is it an hour partition, month partition, along with the range and the timestamp column. Like, they don't want them to have to worry about that. Okay, they want to be able to actually update the table's columns, okay, or update the schema of the table, because in the old paradigm with Hive tables, you generally would have to rewrite the whole table. You want to add a column? It's not like Postgres where I can just add a column. I'd have to rewrite every single data file to include the column and re-register the table. It would not when you're talking about terabytes of data, that's not a lot of fun and not very cheap. And do all of this at scale, okay? So this is where the engineers at Netflix ended up developing Apache Iceberg. And basically the big switch, the big change of approach, the big aha was, how about instead of tracking the table by folders and saying, this folder is the table, how about we just actually generate a list of the specific files that are part of the table? So I no longer have to go to a folder and say, hey, what's in the folder? I already know what files are there because there's a list. There's a list that I can refer to, the metadata. So what is Iceberg when I think about like brass tacks, like what is it? What it is, it's a standard, okay? It's a table format specification, okay? And that means it's a spec of how you write metadata. How do I write information about the table? The idea being is that if everyone writes and understands the same layout of how you lay out this metadata, then multiple tools can read that metadata and understand the table. Like most databases and data warehouses already do this, but again, everyone does it differently. The idea here is to come up with one standard that any tool knows. Okay? And then, but the thing is that just because you create a standard doesn't mean people use it, right? Okay, not everyone's going to want to have to manually implement how to read this metadata. So in this case, a lot of APIs, libraries, were built to help you build that into your tooling. So there's APIs in Java, Python, Go, Rust. So that way, if you're building tooling in these languages, and now a C++ library, it'd be easy to adopt Iceberg because you have libraries that help you read and write to that metadata standard without you having to re-implement all the libraries to do that, okay? So it's about creating a standard and then creating the tools for you to adopt the standard. What Iceberg is not, it is not a storage engine. It's not another place, not another Hadoop. It's not an S3. It's not a place where you store data, okay? Or it's not a file format either. It's just merely the standard for how you write certain files to understand the files that actually do have the data. It's not an execution engine. You don't run queries against Iceberg. Okay, at the end of the day, you still need a query engine, whether it be a Dremio, a DuckDB, a Trino, whatever engine you use, they would understand the spec, and then they would still do the processing part. Okay, this is just saying, hey, this is the table. We'll help you, give you the metadata so you can identify which files you need to read, but then you need to have something else that actually goes and reads those files and executes the query. Okay? It's not a service, okay? There's no server for Iceberg. You don't run some sort of service that's running all the time. It's just a standard. So technically, when you have an Iceberg table, it's just there. There's no service running all the time. You're not paying this compute for this service that's running to have that Iceberg table, okay? Which is nice. There are services that eventually come into play when you start talking about catalog, but for the table, no, the table just exists. Because it's all just files on your storage. So here's like sort of a picture of the basic structure of an Iceberg table. Okay, so I'm gonna go through each of these components and kind of talk about their role in this. So really in that middle part, that's the Iceberg part. That middle part, the metadata layer, that's where Iceberg plays. But in between that, at the top, there's a catalog. And the catalog role is going to be some sort of, typically a separate service. That's a whole conversation in itself. Actually, a good friend of mine, Zoe Steinkamp from ClickHouse, she'll be doing a presentation this afternoon where she'll be going specifically into catalogs, and I'll be talking more about catalogs tomorrow as well for those interested in that topic. But essentially, this would be a service that tracks what tables exist on your lakehouse, and it knows who has access to them. So based on your user credentials, like who do I have access to the sales table? So essentially any tool, again, Dremio, DuckDB, Trino, literally nowadays every tool can talk to Iceberg tables. I think Snowflake bought, I forget the name, Crunchy Data, and then Crunchy Data did a lot of work with Postgres and Iceberg, and I think they just open sourced that work today. I was seeing some posts about that. So that's a thing now. But the idea is that the catalog would be this thing that I would talk to, and whatever tool you're executing the query with would first talk to the catalog and say, hey, catalog, I'm looking for the sales table. Where is it? Okay, and then that catalog would have the name of the table. It's basically just a mapping of table name to the location of where that metadata is in your storage, whether it's S3, ADLS, MinIO, whatever you're using as your storage layer. So in that case, now as the engine, I know, okay, if I want to find this table, the metadata is located right here. And then it would take me to the metadata file. Okay? So the catalog points me to the metadata file, and the way to think about the metadata file, which is a JSON file that sits on top of the metadata structure, is that this tells me about the table as a whole. Okay, what is the schema of the table? How is the table partitioned? What is the history of the table? And that's a really key point. Before, you weren't able to track table history in the Hive paradigm. So you weren't able to query a table as it was like a month ago. Okay, once you made a change, that was the change. That was the table now. But with this, now I can create separate listings or separate versions of the table, kind of like Git has separate commits, and I can now go back and take a look at the table as it was back in the past, also known as time travel. Very cool. Okay? So all that information will be in the metadata file. So then the engine would say, hey, I'm looking to query this particular snapshot. Where can I find it? Each snapshot belongs to a manifest list. Okay, and a manifest list is, well, the name kind of tells you, it's a list of manifests. This is where you get tongue twisted a little bit saying manifest list. So before I talk about what a manifest list is, a list of manifests, let me talk a little bit about what a manifest is. At the end of the day, the table is just a bunch of files, typically Parquet files. So the actual files, the list of files, are in the manifests. So each manifest lists a certain number of files, typically within a partition, and has stats on those files. Now, which of those manifests belong to this particular snapshot? That's where the manifest list comes in and says, hey, these manifests belong to this snapshot. Okay? And the beauty of this is that there's a lot of statistics. It's not just, hey, here's the files. It's here's the files and here's some stats on those files. Because before what would happen, back in the Hive days, I would have to go through all those Parquet files. I'd have to read those Parquet file footers, which still is faster than, let's say, a CSV or a JSON file. But I have to go through each of those files and see, hey, do I need this file at all? Okay, and there's a lot of scanning involved. Here, I can go to this manifest list and I can take a look at the stats for each manifest. I can find things like the range of values. Okay, perfect, thank you. The range of values in each manifest and say, hey, do I need this manifest? No, let's not look at that. And then once I determine which manifests have files that are relevant to my query, I can then go to the manifest, take a look at each file statistics, and then go, do I need this file? Do I need this file? Do I need this file? And at the end, what you've done is you might have, like, let's say 1,000 Parquet files, and you've now narrowed it down to, like, let's say 10. Okay, now I'm only scanning 10 files versus scanning 1,000. That's going to speed up my query performance quite a bit because I'm saving all that time of having to do directory listings, of opening up files, closing files, iterating through the different row groups in those Parquet files. I'm just getting to the files that I need to have data relevant to my particular query. Cool. So once I go through all the metadata, I've now generated what we refer to as a scan plan, a listing of files that I'm planning to scan. And then I just go and scan those data files. So let's see this in action. Okay, now the SQL you'll see on these slides is based on the Spark syntax. Generally, you're going to see mostly the same syntax for the SQL from tool to tool, but there are, of course, SQL is different from tool to tool a little bit, but the way it works under the hood is going to be the same. So in this case, I'm creating a table, specifying the schema. I'm saying I'm using Iceberg. I'm partitioning it. Now, notice how the way I'm partitioning it here, because that's actually kind of neat. Notice I'm using this hour function. So instead of saying, so unlike Hive, where I would actually have to create a separate hour column and then say partition based on that hour column, here I'm specifying saying, hey, I'm partitioning it based on the timestamp based on an hour. Okay, and what the difference is that instead of creating another column in all your Parquet files, what it does, it tracks that transformed value in the metadata, and basically that partitioning will just, the partition filtering will just happen when you read the metadata. It's something that just doesn't exist in the actual data file, so you save that storage, and it's also, the analyst doesn't have to worry about this other column in their queries. They just query based on the timestamp column. When the tool looks at the metadata.json, it'll know, oh wait, this table's partitioned based on an hour transformation of the timestamp column. I know how to handle it from there because it's all explicitly in the metadata. But I would create the table. In this case, I'm creating a table. Okay, and essentially in the catalog, you see that it creates an entry saying, hey, there's a new table called table 1. And then we wrote the metadata. Right now, we're just creating that top level metadata.json because there is no data in the table yet. So there's no reason, if there's no Parquet files, there's nothing to list in a manifest. And if there's no manifest, there's nothing to put in a manifest list. So we just have a metadata.json with a schema and all the high level details of the table. We then tell the catalog, hey, going forward, this table pointed to this particular metadata file. Because everything here is immutable. Okay, we don't really update files. It's always writing new files. And that's how we're able to keep that sort of isolation and consistency. Okay, so then we do another transaction. Let's actually insert some data. So I'm going to insert some data into the table. So now what's going to happen is it's going to write some data files. Then it writes the data files with the data. Then it's going to create a manifest list, or a manifest that lists that file and all the stats for that file. Create a manifest list that lists that manifest for that snapshot, and then a new metadata.json file. And we see it does exactly that. A data file, manifest list, and a new metadata file. Notice, it's not updating the existing one. It's a new one. That's why the catalog is important. Because after, let's say, 1,000 transactions, you now have 1,000 metadata.json files sitting in your storage, which is the right one. The catalog knows because at the end of each transaction, if everything went fine, everything was successful, we tell the catalog going forward, point to this one. Okay? And then that's how you end up having those ACID guarantees come into play. Okay? Because the catalog only gets updated if the transaction was successful. Okay? Now here we're going to do a merge transaction where we're sort of merging the table with a staging table to either update or insert records. Okay? Same deal. We write some new data files, we create some manifests that track those new data files, we create a new manifest list that refers to those manifests, and then make a new metadata.json that now tracks all the different snapshots. So you see now the metadata.json, the newest one, has snapshots 0, 1, and 2. Okay? Cool. Now if I query the data, I'm going to move in the opposite direction. Now I start at the top and I work my way down. I go to the catalog first, say, hey, where's the table? The catalog tells me, hey, go to this metadata.json file, so it points me to the right one. I look for the snapshot that I want to scan. It points me to the right manifest list. I read the manifest list, go through the stats, then go to the manifests, read those, read the stats, generate the list of files that I need. In this case, it's all the files because it's a select star query. And then I go scan the Parquet files. Here, I'm going to actually use it with a filter. So in this case, I'm filtering based on date. Okay, and again, this table is partitioned by hour, but again, since it's based on the order, the timestamp column, it can still kind of figure it out. And again, you don't need to have the explicit reference to specific columns for specific granularities anymore. So in this case, same process, I go to the catalog, I go to the metadata file, I find my manifest list, but now I'm not going to read all the files because using those stats, I can determine that I only need to read one of those files. Okay, so I only read the one file that's relevant to the particular filter that I put on this query. And then here, just to show you that whole time travel bit, here I'm saying, hey, I want to scan the table as of. So I'm not saying I want to scan a particular filter. I'm saying, hey, I want to look at a version of this table based on this timestamp. So now when it's in the metadata.json, it's going to take a look through each of the snapshots and find the first or the latest snapshot that's on or before that timestamp. So in this case, it'll be snapshot 1. So instead of going through the whole data process with the newest snapshot, it does it through the older snapshot. So I'm now scanning an older version of the table. Very cool. So just to kind of see the implications of this, because again, this all originated out of Netflix. One of the systems they had was a system called Atlas, which was a telemetry system that they had. Okay, and generally in 1 month of data, they were generating 2.7 million files over 2,688 partitions. Okay, and the problem is they could only process a few days of data at a time when they were running a query. Okay, it was just not fast. Again, this is when they were still using Hive. So they started developing Iceberg. So let's see the transition from one paradigm to another. So when they were using a Hive table, okay, with Parquet filters, so in this case, it was filtering the data by reading the Parquet footers and determining, okay, hey, I only need these row groups, I only need these row groups in each Parquet file. But it still had to open each Parquet file and do all that. So you would still end up with, so in the actual planning and the amount of sort of units of work, it would still generate about 400,000 plus splits per day, not total, per day that was part of the query. Okay, so just to plan the query, it took 9.6 minutes. So again, that's not executing the query, that's just the planning time for the query. Okay, so they didn't actually even bother running the query because it would take a long time. So now when they switched it over to an Iceberg table, this is only with partition filtering. Okay, because there's technically two things you can do with Iceberg tables. You can do at the manifest list level, you can filter by partitions using those stats. And then when you go to those individual manifests, you can filter by column stats and the individual columns in your filters. Okay, just using partition filtering, you've now narrowed it down to like 15,000 splits total. Okay, so basically you're chopping it up a lot less because you don't have to read as many files. Okay, the planning took 10 seconds. So we went from 9.6 minutes of planning to 10 seconds of planning. Okay, much faster. And then total execution time, 13 minutes. Okay, much better, almost. And now we can make it even better, right? You always want to kind of go the whole, let's go further. Let's go through infinity and beyond. Okay, sticking to staying on theme. Okay, now let's add in the min-max filtering. So that's when we take a look at each column statistics and determine, hey, I'm looking for, let's say, users between 30 and 60. I can see what the range for that column is in each file and determine whether that file is relevant to my query just using the metadata. And once we add that in, it takes a little bit longer to plan because you're doing that additional step. So 25 seconds of planning, but now we've eliminated more files from our scan plan. So now the actual total execution time is smaller, 42 seconds. Okay? Now, going from like 9.6 minutes of planning, which probably would have been in a query that would have taken maybe hours or days, going down to 42 seconds total, that's pretty nice. Okay, the people at Netflix were pretty happy. Okay, and they still are. And I mean, this is like early stages Iceberg. Okay, Iceberg has advanced quite a bit since these numbers. So overall, you get a bunch of benefits when you're using Iceberg for your analytical data. Okay, you can officially make smaller updates. You get snapshot isolation, so you can do that time travel because you have each individual snapshot. You have faster planning and execution. You're going to have reliable metrics because the metrics are in the metadata. Instead of having to separately generate statistics on your table, you're generating statistics every time you actually update the table. Okay, you can time travel. You can actually update the schema. Okay, you can, all engines can use, and the interoperability piece, this is probably the most important piece nowadays. Because it's a standard, every tool can understand the standard, and now you don't have the same kind of problems you had before where maybe you have two departments using two different tools. One team's using Trino, another team's using Dremio, another team's using DuckDB, whatever. They can just share the data. They don't have to fight over what tooling they have to use and standardize on something. They can just say, hey, the data's an iceberg. You use the tool you like, you use the tool we like, and we will just do the work, okay, which is awesome. And then also you can share data between departments regardless of what tooling they use to put the data in there, etc. Okay, and this just allows you to get to focus less on having to move data around and focus more on actually building that BI dashboard, building that AI agent, okay, using this data. You have asset transactions, so you have atomicity, consistency, isolation, durability, and the ability to optimize table. The idea is that usually when you have like a database or a data warehouse, one thing that's happening under the hood is storage management, where it's like optimizing how the data is stored for you, and oftentimes you don't think about it. Once you move to the data lake and your data's files on a storage, who's responsible for that? There isn't an automatic answer to that question, but the Iceberg libraries give you the tools to manage that yourself. Nowadays, there's a lot more people who are building services around that. I'll talk more about that tomorrow, but that's a whole thing there. Now, I do encourage you to get hands-on. If you've never gotten hands-on and like written an Iceberg table or just seen it in action, these tutorials will walk you through the whole process, and you can do them all from your laptop, all through like some Docker containers, so no cloud infrastructure needed. They'll use MinIO as your storage layer. You'll use Nessie as a catalog. Good times. So the first one is just like a basic introduction. The other three will actually walk you through an end-to-end pipeline. So you'll go from like data that's in a Postgres, SQL Server, or MongoDB table. You'll move it over to Iceberg and then build it like a BI dashboard on top of it. So you can see what the whole sort of end-to-end experience is like. And that generally takes about 30 or so minutes total. Cool. And then basically, yeah, that's all that. I'm going to skip. We'll go way back to the beginning for the raffle in case anyone still wanted to sign up for that raffle for that book that didn't. But I will be over there at the speaker library for anyone who has questions. I also have stickers if anyone wants some Iceberg stickers. And again, I will be here tomorrow. I think pretty much the same time. I think it's in a different room though. And to talk more about Iceberg. So I'll talk again a little bit about the spec. So like again, there's a lot of new features that have come just recently in spec of v3. And there are features that are going to come in v4, and I'll talk about the early stages of those conversations, and a little bit about catalog, about optimization, and some of these other things that I kind of alluded to in this presentation. So yeah, and then again, the QR code where you can download the free books. I also have cards for those, so if you didn't have those or you want to give them to a friend, I have cards you can grab as well. Just meet me over there by the speaker library. And otherwise, thank you so much for spending this hour with me. It's been a good time. Thank you. Oh, does anyone have any questions that I can answer since I do have 7 minutes? Hopes, fears, dreams? Yes, go for it. There's people who try to do that. I highly discourage it. Now, this is where Postgres, some of the work in Postgres gets really interesting. So theoretically, with like the PG Lake extension, which has been open sourced, the idea is that you could have your transactional tables in Postgres, just the standard transactional Postgres, but then Postgres can then also handle mirroring them as Iceberg tables for analytical workloads. Because generally, again, the underlying data files are Parquet. That's not going to be ideal for transactional workloads. Like, there's people who try to do it because they want to have all the data in one place, but I highly discourage it. I think the database paradigm as it is pretty solid when it comes, like the multi-tool problem I don't think happens quite as pervasively as it does in analytics, where you have like different teams working with different tools, and you have different teams restoring the data into different systems from different places. So in that case, I think it's definitely focusing on the analytical side. Now, you can build applications on top of it if you're building analytical applications. People do that. But it's mainly for analytical type workloads. And generally the whole lakehouse paradigm or pattern, I would say, is more of an analytical side pattern more than a transactional side. You would take all your transactional data, then land it in the lakehouse for analytical purposes. Other questions? Hopes, fears, dreams? Yes. Ooh, okay, I have some opinions there. Okay, do I see them like I don't see like a merge, a code base merge. The reason just being just because of the way the two projects are governed, it wouldn't work in the sense that Delta Lake is an open source project with lots of contributors, but it's mainly guided by Databricks, while Iceberg is an Apache project, which Apache has very strict governance rules about sort of like how the influence over the project is divvied up. But you're already seeing better collaboration between both communities, where basically people are, and that's the beauty of open source, where everyone can sit there and see what are the good ideas from different projects and start adopting them. So you are going to see both projects, including other projects like Hoodie, Paimon, Duck Lake, who are all operating in this sort of data lakehouse space, taking a look at these different ideas and saying, okay, hey, what are the good ideas of each other and how can we adopt them? And you're starting to see that. For example, in V3, one of the new features was a feature called deletion vectors, which is a way of storing row level updates that originated out of the Delta Lake project, because that particular pattern of like, hey, how do we track minor updates when you're doing frequent inserts or frequent updates to the table? How do you do that efficiently? First, Hoodie was the first person to kind of attempt that. They did it one way, then Iceberg did it another way, and then eventually Delta Lake came out with deletion vectors, and then everyone learned from the mistakes of the past, and so basically now Iceberg is like, well, actually that's a pretty good way of doing it, and now that's part of the Iceberg spec as well. So I see them getting closer. I don't see them becoming the same project for different governance reasons. Also, there's just also certain differences in sort of their architectural assumptions. So like in Delta Lake, it's a lot more like Git, where basically each snapshot is not a list of files, it's a difference, like, hey, add these files, subtract these files, and then you iterate through these log files to create the list of files, versus Iceberg, you create a separate list in each snapshot. There's pros and cons to both approaches, and because of that, I imagine both will exist, and those as two different things, but they will be closer. Cool, that's the short but still long version of my opinion. Any other questions? Once? Okay, but again, if you have any other questions, I will be at the speaker library. Again, I always appreciate so much to attend. Do stay in touch. If you haven't connected with me on LinkedIn, please do. And then if you extra want to follow what I'm doing, feel free to also follow me on Substack or Medium, where I spend a lot of time opining on this space. With that, thank you very much. I'll see you all tomorrow. Okay.